Hello everyone, and welcome back for another webinar Wednesday. Today we're talking about galvanic encasements and cathodic protection jackets, focusing on marine structures and non-marine structures. This series is brought to you by the National Concrete Bridge Council. They are a council of allied industry organizations dedicated to promoting quality in concrete bridge construction, gathering and disseminating information on design, construction, and condition of concrete bridges, and establishing communication with federal and state departments of transportation, city and county public works departments, and consulting engineers, and provide information on behalf of the concrete industries to codes and standards groups. You can see all of their members there on the left side. This is the fourth episode in our 6-part series. Up next month is going to be extending the bridge life using targeted cathodic protection, followed by surface applied cathodic protection. You can find more on those and where to register at our website at wesafestructures.info. You can follow the link on screen there. Today we also have a challenge to you all. If you are interested in winning a $100 Amazon gift card, we'll be giving that away to the best question asked. There are a few rules in our Q&A system here. By default, you do show up as anonymous. So if you want to be considered for it, you're going to have to put your name in there so we know who to contact after the show. You can ask as many questions as you want, so please ask away. And like I said, the best question will be picked by the presenter. And that presenter is Mr. Jason Chodacek. He is Vector Corrosion Technologies marine specialist, and he's a NACE cathodic protection technician. He's over 25 years of experience building and designing various cathodic protection systems, and has been also working in the Florida area, doing a lot of marine work as of late. And with that said, I'm going to let Jason take it away.
Thank you. So I'm going to go on just here. Thank you everybody for joining, and I'm just going to move on to our outline here for the presentation. My Windows computer did an update here earlier and caused some issues with my PowerPoint, so I hope it runs smoothly. If not, we'll just switch over and have Ben run through the presentation while I speak, but cross our fingers here. So for the outline, I'm just going to do a brief introduction to corrosion, just talk briefly about corrosion, how it works, and why our reinforcing steel, or all the steel that we use in our structures, actually corrodes. And then I'm going to move on to some of the past solutions for pile protection, which is just going to include a variety of different things that I'm sure a number of you have come across in the past, and how basically the majority of these solutions just did not address that corrosion problem. Another thing that I'm going to talk about as well is just your environmental conditions or your exposure conditions. So depending upon which section or which part of your pile is in a certain environment, this is actually going to dictate basically what kind of corrosion or the amount of aggressive corrosion that you're going to have in your or on your pile or on your structure. So everything from a submerged section all the way up to an atmospheric section. There's all chlorides that are present there, but there's just varying different amounts of oxygen and moisture that's present as well. Then I'm going to go into a number of the different types of cathodic protection systems that's available for all the different types of piles that are out there. Everything from steel piles all the way to concrete piles. And along with this, I'm just going to talk briefly about some of the advancements or some of the improvements for bulk anodes that are used on the underwater or the submerged portion for these cathodic protection jackets. Then this is going to bring me on to some of the sheet pile protection. So obviously we have sheet pile walls out there that are typically have a coating. Some of them don't have coatings on it, and we're going to go through some of the available options in terms of CP that's available for these for the sheet pile. And then lastly, we're going to get into encasements in non-marine environments. So all of the areas where you basically have corrosion on your structures, but we're going to be doing an encasement on it where you actually do not have access to, or it is not in the submerged portion of a marine environment as well. So I'm going to move on here to the corrosion cycle. And I think this is just a good slide because what it does is it demonstrates why our reinforcing steel in our structures actually want to corrode. So in the beginning, we go in and we get this iron ore out of the ground. It's super stable, right? It's in the ground. We're going to go in and mine it, and we're going to pull it out of the ground, and we want to make iron out of this. So what we're going to do with this is we're going to basically push or put a bunch of energy into this iron ore. So we're basically elevating this iron ore up into a material or into iron. And so we pushed a huge amount of energy into this iron. And then all that happens is then we take this iron and we put it into our structures, whether it's embedded in concrete or whether it's actually just an exposed steel structure. But when we put it in there, all that happens is this iron that we've pushed all of this energy into, all it wants to do is go back to the original form that it was in the ground, essentially. So it just wants to go back to rust. And so this is kind of the corrosion process that's happening within our structures. And I'm just going to go through a brief slide here on the corrosion process of steel in reinforced or steel in concrete. And so this corrosion process is it's an electrochemical reaction, of course, and it requires a number of things for this to occur. And so a good way to remember this is ACME. So we have A, so A stands for anode, or the section loss, or this is the area where we actually have the rusting or the corrosion of our reinforcing steel. So that's our anode portion. That's the portion corroding. You can see it over there on the right side of the slide. And then we need, for the letter C, obviously, we need our cathode, right? So this is the area that is not going to corrode, or it's going to be the area that's essentially protected. And you can also see it over here on the right side. So we have our cathode, we have our anode, but now we have to have basically a metallic path or a metal. And so if you look on here, you can see that there's a number of bars and stirrups and so forth, and there's going to be tie wires. So you have to have this metal or a metallic path in order to complete this circuit between the cathode and the anode. So it has to be electrically connected. So that's what we have there. And then lastly, we have E, which is our electrolyte. And our electrolyte is basically just the medium which we have our reinforcing steel embedded in. So in this example here, our rebar is embedded in concrete. So our concrete is our electrolyte. If you had a steel tank that was embedded or buried in the ground in soil, your soil would be your electrolyte, and the same goes for seawater. You take sheet pile, put sheet pile or a concrete reinforced pile in water. Now your water becomes your electrolyte as well. So then I'm going to move on here just to talk about, sure everybody's fairly familiar with concrete properties, but it's very high in pH. When we first pour or build a structure, our concrete has got a very, very high pH. And then it basically starts, when it gets exposed to the environment, then this pH can basically decrease. It's also very hard. As we know, it's very hard, but it's also very porous, right? If you pour any water or any liquid or anything like that on concrete, it actually ends up, you can see it getting soaked up into the concrete as well. So it's also great in compression, as we know, and it's also poor in tension. And because of that, because it's poor in tension, it requires reinforcement. And so that's the whole reason that we're putting rebar or any sort of reinforcement into our concrete, is because of that poor tension as well. So what ends up happening is when you embed, so over here on the right side, we have a piece of steel that we've embedded in new concrete. And when we embed reinforcing steel in new concrete, basically it instantaneously, or it automatically has a protective passive layer that actually surrounds your reinforcing steel. So any sort of new structure where you're pouring concrete around steel, you basically get this passive oxide layer that protects your reinforcing steel, and it actually prevents corrosion from occurring around it. So good quality concrete, you basically get a good protective layer or passivation layer around your reinforcing steel. And now what ends up happening is actually over time, this protective layer can be disrupted or can be taken away. And there's a number of different things that do it, but in our environments or in our type of work that we get involved in, it's typically carbon dioxide or CO2 or chlorides, right? So especially in a marine environment, you can get chlorides, or for an old structure, it can be carbonated over time if it's a very, very old structure. But basically, both of these will break down that passive oxide layer, and it's going to actually now allow your reinforcing steel to start to corrode in your concrete as well. So now I'm going to move on to, so one of the other things that I want to briefly talk about is brackish water and corrosion. And so what ends up happening is, so in a marine environment, you can be exposed to brackish water, and the brackish water may not have very high levels of chlorides in it. So it may just have some moderate levels of chlorides, nothing that's near the point that's really going to cause a huge corrosion issue, say for exposed steel. But what ends up happening is with the chlorides, basically because of the concrete being very porous, this brackish water basically goes in and out of our concrete surface here and basically goes in, and due to this repeated wetting and drying cycle, basically what ends up happening is the chlorides remain in the concrete. And so when it dries again and then it re-wets, so you can actually have very, very high elevated levels of chlorides in your concrete, even in brackish water where you actually don't have very, very high salt concentrations as well. So some of you may have come across this where you're actually out in a brackish water area where there's not a lot of chlorides in the water, but you can still see significant corrosion, especially on reinforced concrete structures out there due to that, concrete basically absorbing that water over and over. So chloride-induced corrosion, just here's a few pictures of them. Obviously, it breaks up that passive oxide layer, like I mentioned. There's a number of areas that or sources for these chlorides. Obviously, marine environment that we're going to be talking about here is a big one for us. And then there's a number of other areas that you can get chlorides from as well. So one of the things to think about in this is chlorides are never actually consumed in this process, so they're always there to continue that corrosion process or that corrosion cycle. So they never get consumed, so they're always there regardless. The next thing I'm going to move on to is pile exposure conditions. I mentioned this in the introduction, and so it's going to dictate basically what type of a cathodic protection system you're going to use on the structure. So a pile can be exposed to a variety of different environments, and they can vary anything from our submerged or our underwater section all the way up to our tidal zone or our regular kind of wetting zone. So this is where you have your tides that are constantly going up and down multiple times during the day, so your structure's getting wet and dry at the same time. And then we're going to move up into our periodic or kind of our splash zone. So this is either, storm events, it can be wind, it could also be boat traffic. So this area here also receives, fairly significant wetting and so forth as well. And then from this, we're going to move up onto the pile. We're going to go into our dry area or atmospheric area. And this is the area where, especially if you go to a beach and you can see waves that are crashing, you can see basically a mist of chlorides that are floating in the air. And this is the part of the structure that actually gets exposed to this as well. And so one of the things to think of is even though, if the pile is not exposed directly to water, it still can experience corrosion even higher up on these dry or these atmospheric areas. So basically everywhere on this pile, corrosion can occur. The most extreme portions are going to be the tidal zone and that splash zone right in that middle of the pile where you have a lot of chlorides and it's wet all of the time. So now I'm going to just move on to some of the past strategies that have been used to basically prevent corrosion from occurring on steel piles, or to extend their lifespan. So the first one is uncoated steel, right? So you just have a certain thickness of steel, you know it's going to corrode, so they come in, and whether it was pipe piles, sheet pile walls, number of them, it's just an uncoated steel pile or steel, and it's just left to be exposed to the elements, and it's going to corrode. Then the other one is coated steel piles as well. So you can put coatings on your steel piles or sheet pile walls as well. But what ends up happening is you end up getting coating failures, right? So whether it's from holidays, from when it was the coating was applied, or during installation. During installation, obviously the sheet pile or these pipe piles can be damaged just through the driving operations, and also just bringing them out to site as well. So you get these coating failures, and then what ends up happening is obviously you get this corrosion that occurs. So you have corrosion occurring, and these are very, this type of corrosion is very difficult to repair. How do you come in and repair this coating? You'd have to come in with some sort of a cofferdam or some sort of a wrap, and then you still have all of your salt water and chlorides and so forth that's still available for corrosion to occur. So another one is fiberglass jacket. So basically it's a fiberglass jacket that is placed around a pile, and then it is filled with an epoxy grout. And what ends up happening with these as well is, so the hope is that you would put the epoxy around, or the fiberglass jacket around with the epoxy grout, and you were hoping to reduce basically the amount of chlorides and the amount of oxygen to that portion of the pile. And what ends up happening is moisture still present in there, chlorides are still in there as well, and corrosion ends up actually occurring in behind that jacket, behind that fiberglass jacket. And it's very difficult to see any of the damage that's being done behind it until it gets extremely bad. And if you can see here on the left, this is actually a jacket that was removed just a couple of years ago. It was removed, and that was what was behind it. So it wasn't evident that there was a huge amount of corrosion that was taking place, but once the jacket was removed and the epoxy fill was actually removed, then you could actually see all the corrosion that had been taking place. So, and then moving on to another past strategy for it is very similar to the epoxy. The fiberglass epoxy fill jacket is just a fiberglass or stay in place form concrete filled jacket. And you can see here, so it was a very similar thing. So it's just a stay in place fiberglass form that's put around the pile, and then it's filled with a flowable cementitious mortar or grout. And what ends up happening in behind this as well is there's still chlorides, there's still oxygen, all of this stuff still remains in behind the jacket, and corrosion can still continue. And this is the bad thing about it is corrosion continues in behind this jacket, and it's not visible for you when you come out to do an inspection on it. And it can be fairly aggressive in here behind it before you actually see any sort of damage or delaminations to this fiberglass jacket as well. So jacketing is obviously is the most common repair strategy that we come across when we're out there. I showed you just a few of them here in the past, some of the past kind of jackets that were done without any sort of cathodic protection. And so there's been a number of studies and so forth that have been done on basically jackets or concrete jackets that have been placed around piles. And basically they found out that corrosion still occurs in behind these jacket systems without CP on it. And so the number of owners and entities and states and so forth have now basically included in any sort of a jacket or a jacket overbuild or jacketing situation, they want to include cathodic protection in it. So some sort of cathodic protection has to be included in it just because this corrosion continues. And so with that, what ended up happening was there was basically a cathodic protection jacket system that was developed for the underwater portion, or this tidal zone portion that I had just talked about on the previous slides. And so We have a lot of salt water. We have a lot of so we have a lot of low resistivity in here. So it's very, very easy for corrosion to occur, and when it happens, it just starts to continue, and it continues at a high rate as well in here. So one of the CP jackets that was actually developed, Florida DOT in the 90s actually developed a zinc mesh, an expanded zinc mesh jacket that was actually placed inside of a standard fiberglass stay-in-place form. So this zinc mesh is actually attached to the inside of the fiberglass jacket, and it has basically an open bottom, so it allows water to basically go up inside of this jacket. And then along with this expanded mesh jacket, there's also a hull anode, or a zinc hull anode, that was attached to the underside of the jacket, approximately about 2 feet below the bottom of this jacket. And this hull anode was designed to protect the area, or that submerged portion of the pile. So we have our seawater that's below there, and it was designed to protect that area. So here's just kind of a detail of how it works. So we have our wet zone, we have our underwater zone, and what ends up happening is some of the water basically enters the bottom of this jacket, and this salt water is actually going to saturate the zinc mesh and basically activate the zinc mesh and basically provide corrosion protection or cathodic protection to our reinforcing steel within this jacketed area. So one thing to note is that on only the areas where it's basically where you have your salt water that has entered the bottom of the jacket is going to get the area of cathodic protection. As you start moving up higher and higher on the dry zone, the salt water is not available anymore. So what ends up happening is the zinc starts to passivate, and there's a couple of slides coming up that I'll talk about this. As I mentioned, you're going to take that hull anode that was placed underneath of the jacket, and this is going to provide cathodic protection to everything in the water zone. So we have our electrolyte that we had talked about before. So we're going to use our salt water here as our electrolyte, and this bulk anode is going to protect the pile in our submerged zone. So now I'm going to move on to basically, so we have our underwater area, or our submerged zone. We're going to get some salt water that's moving up into our zinc mesh here. And as you start to move higher and higher and higher on the elevation of the zinc mesh, you're getting less and less activation of our zinc. And the reason for it here is if you look over on the right side, we have our corrosion rate versus pH. And once you're concrete in your pile, typically, once you start to see corrosion occurring on your pile, you're probably going to have a pH of around 11 or 12 in there. And zinc, when you have zinc that's embedded in concrete, you can see here on the right side that the corrosion rate of zinc, or zinc only starts to corrode either in a very, very high pH environment or a very, very low pH environment. So when we have our zinc that's embedded in this concrete, the zinc does not want to corrode, and that's why we're relying on that salt water. We're relying only on that salt water to activate the zinc in this case. So what can we do to increase this activation zone, or increase this kind of tidal or splash zone? Because this is the zinc mesh is very effective, in the smaller zone down at the water line or in that tidal zone. But what can we do here to basically activate the portions, or the elevated portions of our jacket to keep it actively corroding, or to keep the zinc in a corroding state? And so can we increase the exposure to salt water, right? Can we increase this wetting zone? And then if we can do that, we're going to stop the zinc from passivating. And by doing that, obviously, we're going to increase the performance of this jacket and increase the area, or elevate the area of our cathodic protection. So some of the improvements that have been done to the zinc mesh jackets here are now going to allow it to not only protect everything in the tidal zone and the underwater zone, but we're going to actually move up into that periodic zone, or where, storm events and so forth, or boat traffic, just periodic splash zone. So what we're going to rely on here is, instead of a tidal jacket, it's a tidal plus jacket. And basically what we have is we have the concrete, and we have an anode that's going to be embedded in the concrete. And basically, it's a very, very similar system. So it's a cast zinc anode, very similar to the expanded zinc anode, except this is just a larger bar of zinc. And then there's a wicking fabric that's placed around it. And this wicking fabric is there so that the salt water can flow up and down this fabric and using capillary action. And this allows the zinc to always remain in a wet state, or it's always wetted with salt water. So this is going to keep it in an active state. And then if you remember back to the pH versus the corrosion rate chart, it's also going to act as a protective barrier between our pH, or our lower pH of our concrete, which is roughly around 11, and our zinc. So we do not want our zinc to be in contact with the concrete within that jacket. And by doing that, it's going to allow the zinc to remain in a more active state and basically provide a higher level of cathodic protection for the jacket. So, and then this is just kind of a detail of how it's installed or the parts of the system. So basically you have a wicking fabric that's attached to a pile. It is hung on a pile, and you're going to determine in your design whether you're going to use 1 per face or 2 per face, and depending as well if it's a round pile. So you're going to do a design to figure out how many anodes are going to be required, or Tidal Plus anodes that are going to be required. There's also going to be the stay-in-place form that's going to be used. And then as well, we're going to use a bulk aluminum anode for the underwater portions as well, for the submerged portions. So typically we were using a hull anode, but now we're also going to use a bulk aluminum anode that was designed specifically for cathodic protection on piles, and we're not just pulling an anode off of the shelf. So, and then one of the other things that you can have as well is an optional junction box. So you can basically run these wires from all of the anodes to the junction box, and then you can have some wires from your reinforcing steel to the junction box, and that allows you to monitor basically monitor the jacket system to see how much current it's actually producing, and basically measure the life expectancy as well of the system. It's also used for energizing, turning on the jacket, and collecting some data up front to show that the jacket was also installed appropriately. So, but with all of this, we're getting some increased cathodic protection for it. And here on the next slide, I'm going to just show you how it works. You know, what's the differences here between the Tidal jacket. So for the Tidal Plus jacket here, we have our wet zone that's down below, same thing. And what ends up happening is we have our wicking tail. So these tails are basically sticking out the underside or in the wet zone of the pile. And what's going to happen is these wicking tails are going to actually allow the salt water to wick up and go farther and higher up on these zinc bars, and basically completely saturate these zinc bars and keep the zinc in an active state. So the fabric, and again, the fabric is also going to help isolate it, stop the zinc from actually contacting our concrete mortar and passivating that way. So what we've been able to do is we're able to basically bring the salt water higher up in the environment or within our jacket system. And so now we can actually activate the zinc higher up on this jacket system as well. So, and here are just some of the components for it. So on the left side, you can see the solid zinc bar. So it just has a tie wire that's cast inside of it, and then it's placed in wicking fabric, and that is what's placed around the pile. And then in the middle here, we have our bulk anode. There's just a typical bulk anode assembly. This one here is showing the aluminum anodes now for it instead of the zinc anodes as well. And then, as I mentioned, you can have an optional junction box. And so you can see in here, the junction box, there's a shunt. That's basically just a low resistance resistor. So you can go in and measure the voltage across this resistor, and then you can actually calculate the amount of current that your jacket or your cathodic protection jacket system is producing. As well, you can see a link bar. Basically, that's just a mechanical switch. That's what actually energizes or turns your jacket system on. And then there's a number of red wires and black wires. Red wires being our anode wires, either from the bulk anode or from the Tidal Plus anodes. And then the black wires are all structure wires, rebar wires. or even external structural cages. If you're adding another additional cage of reinforcement in it to make it a structural jacket as well. So as I mentioned, and another advancement for it with the Tidal Plus was moving from a 48-pound bulk zinc hull anode. So traditionally, a bulk hull anode had been used. So these are anodes that have been used obviously on boat hulls before. They were thought to be used because it was a zinc anode, and they needed compatibility with the zinc mesh that was inside of the jacket. Another thing is typically what had been used in the past was there was one hull anode used for every type of pile out there. So whether it was a very, very large pile, if it was a very large pile compared to even if it was, so if you have a 14-inch square pre-stressed pile all the way up to very large drill shaft piles, that are 60 inches in diameter, one zinc hull anode was used. And then as well, what about your water column? The depth of the piles, do you only have 10 feet now down below to the mud line, or do you have 40 feet? And all of this, so the more exposed pile that you have in that water column, the larger or the more cathodic protection is going to be required to protect that area as well. So one of the things, this is some of the things that had been looked at. So is one hull anode sufficient? And as well for these larger, longer piles. And then another thing that is becoming more predominant as well is just zinc toxicity. So if you maybe have certain estuaries or even certain ports where you have a lot of marine environment, zinc toxicity is becoming a thing, and aluminum is a much more environmentally friendly alternative to zinc for it. So what ended up happening was basically 25-pound bulk aluminum anode was specifically designed for pile jackets for it. So it was a custom design, shape and size, and this is basically going to fit the majority or 90% of the piles that actually receive cathodic protection out there. And one of the worries was, is aluminum going to be compatible with all of these zinc jacket systems that are out there? And so from all of the tests and trials that have been, field trials that have been done, the aluminum bulk anode is actually compatible with these systems as well. So another thing is aluminum is actually more efficient. So when you're having an anode, a bulk anode that's actually exposed to seawater, aluminum is much, much more efficient and has a higher current density compared to a zinc hull anode. So we can come in and we can use a smaller, basically a lighter aluminum anode that's going to be easier for installation. You're going to get more cathodic protection current out of it and a higher current density out of it as well. And then on top of it, for those instances where the zinc is maybe an environmental concern, it's also aluminum is a much, much better option for that. So again, the anode, the aluminum anode was actually designed from data that was actually acquired from the field. So the anode was actually sized for it, put in, and then the appropriate size anode had been made. And like I had mentioned, 25 pounds seems to fit about 90% of the piles. So when I say it fits 90% or so of the piles that are typically being jacketed out there, that leaves another 10% of the jackets on piles that it wouldn't be. So this is one of the things that you need to do is when you're doing a CP jacket design or doing the specifications for it, you have to make sure that the bulk anode is part of the jacket design. So if you have a very large drill shaft pile, it's 60 inches in diameter and it's going down 40 feet into the water, you're likely going to need more than one bulk anode. So just make sure that the bulk anode is actually part of the jacket design in the design phase. So you're not only just going in and designing for how high the jacket's going to come out of the water, but you're also going to make sure that you're going to include the bulk anode in on this. So, and again, it's all depending upon how much of the pile is in the water column. Longer pile, larger pile, you're likely going to require 2 bulk anodes for this instead of 1. So I'm just going to go through a couple of pictures here on the installation of the Tidal Plus jacket. So it's a very similar concept as to the Tidal jacket. And what we have here is we have a pile where this is actually a structural jacket on the left side here. So you can see our structural cage. So that's a new additional reinforcing cage that's been placed around the pile. The anodes were hung before the reinforcing cage was placed. And you can see all the wires that are just being hung on the pile cap here, getting ready to be installed into the junction box. Here as well, you can see there's some pumping tubes on the left side as well. So they can either be filled by trimming method using pump tubes like this. Basically, you're filling from the bottom up, and they have certain ports in there that break away as the pressure increases. Or you can use traditional pumping ports on the outside of the jacket that are typically staggered at 2 feet on center, or sorry, 4 feet on opposite faces of the jacket. So the jacket's just being placed around, some temporary shoring and bracing is being put on it. And then it was poured. The junction box here on the right side, you can see the junction box has been installed and all the wires have been run into the junction box. So again, here's kind of a typical detail of a junction box. So as I mentioned, the red wires are for all of our anode wires. So these could be coming from the Tidal Plus anodes. And if you see on the right side of the red block, there's a larger red anode there. That's going to be from your bulk anode. So all of those red anode wires are coming up to a block, a distribution block. Then that one block is going to be tied on to a shunt, and that's what's on the left side there. That's that little green tab on the left side. So it's a known resistor, and then from that side, it's going to go all the way over and get connected to our cathodic side of our jacket system, so our reinforcing side. So on this example here, we have 2 wires. So we have 2 wires going down, connecting to our reinforcing steel. And for this, we have 2 because you want to have some redundancy in there. So during your installation, if one wire becomes disconnected or broken, you still have another wire. Now, for a structural cage, you would also have additional wires that would be coming up to this cathodic protection, or sorry, to the black bar on the right side there as well. So, and then on the outside, or the far right side there, we just have our a stainless steel bolt that's coming out. So basically that's an external structure connection. So you can come up to this junction box when the cover is actually on it. You can come up and take readings. So you can take voltage measurements across your shunt, and you can also do some energizing measurements from it as well. So then there's no need to actually have to remove the lid from the junction box. So in terms of performance, I mentioned that we are getting a performance jump over this, the Tidal Plus versus the Tidal jacket. And you can see here that the Tidal jacket, or the first generation mesh jacket, we're getting, a few milliamps of current that are coming out of the jacket versus what we are seeing here with the Tidal Plus. So we're getting a significant improvement in performance, or in cathodic protection output for it. And not only are we getting increase in performance in just the tidal zone, but we're also able to extend that protection, or that cathodic protection zone, higher up within the pile, much higher up on the pile than just our typical, or than the typical tidal jackets. So now I'm going to move on to what happens when we move up into this atmospheric area. So all the previous areas I was talking about, we actually have access to salt water. So we were relying on that salt water, or using that salt water in both the Tidal and the Tidal Plus jacket systems to activate the zinc. If you remember, if we embed zinc in concrete, the concrete does not have a high enough pH to keep the zinc actively corroding. So we had to rely on the salt water. So we needed that salt water to keep it active. But now when we move up to this atmospheric area, or the dry area, we do not have access to that salt water. And so what ends up happening is without that salt water, we're going to have to rely on something else besides the salt water that's in the environment. So this is that corrosion rate versus pH graph again as well. And so if we look at the corrosion rate of zinc on here, we can see that zinc corrodes either in a low pH environment or in a high pH environment. So we're going to obviously want to use a high pH environment for it, right? So low pH, if you have a low pH environment, steel corrodes in a low pH environment. Steel is actually protected in a high pH environment. So you're going to want to use a high pH to activate the zinc, because our corrosion rate of zinc is much higher in a higher pH. Plus, then it's not damaging or detrimental to our reinforcing steel as well. So what this technology is basically, it's very similar to the Tidal Plus jacket, but it's called a distributed anode system. It's an alkali activated jacket system, and it does not require salt water for it. And it has an anode very similar to the Tidal Plus anode, but instead of being encased or surrounded by a wicking fabric, it's actually encased in an alkaline mortar. So it's encased in a very, very high pH mortar, very similar to how a AA battery in any of your remotes that you would use for your TV. The zinc shell is actually basically encased in a high alkaline activated mortar to keep that zinc shell in an activated state. So we're doing the exact same thing here. So we're just basically embedding the zinc in a really, really high pH mortar. And we're going to use the same stay in place form as well. And that high alkaline mortar keeps the zinc actively corroding, and we do not need salt water for it. So this is an area where if you're looking to protect something higher up, you can install this type of an activated jacket higher up outside of those elevations where you don't have access to the salt water for it. So we don't need salt water as well. You don't need, this can work in a saltwater environment as well. It can also work in brackish water. As I mentioned before, you may end up having brackish water where it is actually does not have high enough chlorides in it to keep zinc in an active state, but yet you still had enough chlorides within your concrete within your concrete pile that you had corrosion occurring. So this is another example. You can use the activated jacket in these brackish water environments, and even in freshwater environments if for some reason you have any sort of organic corrosion or something that's happening there where you have a corrosion problem as well. So, and again, dry land, of course, and then again, if you're using this in a brackish water environment, you can use a bulk anode for protection, because you can extend this jacket down into the water. Another option that you can do is you can use a combination of, you can use this activated jacket with one of those Tidal Plus jackets as well. So you could use the Tidal Plus jacket in the salt water or in the water portion, and then as you move up higher in these higher elevations where you don't have access to the salt water, you can then use the activated or the alkali activated jacket in this in these elevated portions. So again, we have our wet zone. There is no water going into the bottom of our jacket system. And we have our alkaline mortar that's surrounding the anodes. So the zinc is only being activated by this mortar. It's not being activated by the salt water. And again, we're relying on this high pH of this mortar to activate the zinc. And at the same time, it's not going to be detrimental to the end of any of the reinforcing steel that we have in the jackets as well. So here's, I'm just going to go through a few pictures of the installation of the system. Again, it's going to be very similar to the Tidal Plus system, except that it's not going to actually be in the water. So in this example here on the right side, you can see there's some fiberglass forms. There's some alkali activated anodes that are attached to this fiberglass stay-in-place form. And this was actually for a FDOT project here used in just north side of Miami here. Again, if you're using this in conjunction with a Tidal Plus jacket, or you were bringing this down to the water line, say for a brackish water environment, you'd still want to use an appropriate bulk anode if needed. So Here's the structure. So this is obviously when it was finished. You can see on the map where the structure was located. It's in the intercoastal waters here. It's a little drawbridge. And then here's just some detail of it. So there was an additional reinforcing cage that was actually attached to it. And then the anodes were going to be just placed around these columns as well. And then so there was some welded wire fabric also being used just to help for confinement. And then the anodes were being placed inside of here. And then the jacket was just filled with mortar. So first thing you do is when you come in, remove any of the delaminated concrete. So you can see here, the laminated concrete was removed, and then you can see there's a continuity groove. That groove that goes around that column, you can see it on the first column, and even the previous or the backside, or the columns in the background, you can see it. So that's our continuity groove, and so that's actually being made so that you can check to make sure that all of the reinforcing steel is continuous within that column. So if you remember back to the beginning of the presentation here, we had that metallic path. We want to make sure that there's a good metallic path between all of our reinforcing steel within the structure. And you can see there's a small wire there that was actually attached or welded to each of the pieces of steel within that column, just to make sure, just to ensure that they had good continuity or good metallic path. So again, we have our sand place forms with our anodes attached. The jackets are placed around the column, and they are braced appropriately to keep shape. And you can see that there's pumping ports that were on this jacket as well. Alternatively, you could have used also a tremie port. You would have ended up using a few different tremie pipes in this as well. When using a tremie pipe, just be sure that the contractor has them secured and they're not going to move and knock a bunch of the wires around or knock a bunch of the anodes around as well. And on the right side, you can see there's a junction box that was being used on this. So then here, this is after the mortar had been pumped into the jacket, and it was set and the forms were removed, and you can see the pumping ports on the sides of the jacket there, and the junction box is still open, so they were coming in and energizing the jacket system. So basically turning the jacket system on and verifying that they're getting cathodic protection out of this jacket system. So again, this jacket here does not rely on salt water. It only is relying on the activating mortar that's surrounding those anodes within that jacket system. So again, so this is a finished picture of the pile. So you can see the tide at low tide and high tide. So the tide never gets up to the jackets here. So it's just being activated by the anodes within the jackets. One thing to note here as well is not only did the columns receive cathodic protection from these anodes, but those footers that you can see the columns sitting on, those columns were actually receiving CP from those anodes as well. So they're able to pass a huge amount of cathodic protection or CP, very, very similar to a powered system in this case. So these were all jacket systems for basically for bridges or structures that were within kind of a marine environment as well. And I'm going to move towards now just to talk a little bit about steel structures in a marine environment. So what about any protection for steel sheet piles in a marine environment, right? So what we have here is obviously we have coating failure. Obviously the sheet pile wall has experienced a ton of corrosion here. It's probably well beyond being fixed or repairable. And so typically what is done in these circumstances is you would have some sort of a concrete cap that would be on the top of it. And then you would also have some bulk anodes that would be attached to your sheet pile wall within your submerged zone. So this is also a very aggressive area for corrosion. You want to make sure that you'd have a coating on here, because if you have a good quality coating on here, then you're going to require less anodes. So even from day one, when this sheet pile is installed, you want to make sure there's a coating on it, good quality coating, drive the piles, and then you're going to want to make sure that you also design and install a galvanic cathodic protection system for that submerged zone. It's a very aggressive environment. There's going to be holidays, chips, all that sort of stuff from driving the piles. You're going to want to install bulk anodes on it right from the beginning, right when it's new, and it's going to extend that service life of that sheet pile wall tremendously. Now, what ends up happening is you have this tidal zone. So this is that tidal zone that's above the bulk anodes, and it's a very, very difficult area to protect. So you get a lot of coating failures in this part or in this area, as I showed you in the previous picture. So what can you do to actually rectify this situation once your coating starts to fail and you have corrosion that's occurring? For example, what can we do to rectify this situation or to help it, to prevent it from getting to that situation? So one of the things that you can do is there's a jacket system for sheet pile, and it works basically exactly the same way as the tidal plus jacket systems worked in the previous slides that I showed you. So we have our tidal zone here. This is going to be our tidal zone. So you're just going to have a standard fiberglass form that's going to be molded or made to fit the geometry of your sheet pile wall. And then you're going to throw in some anodes within this stay-in-place form. So this is the tidal plus anode. It's going to rely on that wicking technology or the wicking, making sure to bring the salt water up to keep that anode in an active state. And then everything that is below that jacket, you're going to want to put an anode on it. So in this case here, the anodes were actually attached up in the jacketed zone. This just saved the contractor from actually having to use divers to weld the anodes on. But anodes can also be welded on traditionally, like I'd shown you in the previous photograph. So just a regular bulk anodes that are just welded to the sheet pile wall. But the bulk anodes are going to protect everything below the water line, and then the jacket system here is going to protect that tidal zone or that really, really aggressive zone as well. So, and this is basically everything here for a marine environment. And I'm going to move on now to encasements. So this is for things that are not in a marine environment. So it's going to use the very, very similar anodes that were used in these jacket encasements or these CP jackets. So you can think of this as just a very, very large atmospheric jacket that's going to be used in an area where it's a non-marine environment. So this is actually an abutment for the Ohio DOT. And so traditionally what they would do is they get some spalling that would happen up here. So you have your approach slab, you have your existing bridge deck, you have an expansion joint above it. That expansion joint fails all the time, so you get a lot of de-icing salts and chlorides that are coming down onto that abutment wall, and you end up getting corrosion occurring. So this is just the repair detail for the for this abutment wall as well. So here they use some supplemental reinforcing in it as along with it, and then they use some embedded galvanic anodes. So in that blue area, they threw a little bit more steel in there, fixed any of the bad steel. And then they threw some small, discrete embedded anodes that went into there. And what ended up happening was it's a very aggressive environment. So even though they did the repairs up top, so they addressed the repairs up top, what ended up happening is when they came back after doing the repairs, they come back and there's huge amount of corrosion that's still occurring on this abutment wall. So what we're going to do is we're going to do something very, very similar to that atmospheric jacket that we used on piles. So all we're going to do is we're going to come in, we're going to add, in this case, we're going to actually add some new reinforcement. So we're going to basically add kind of a structural cage of reinforcing steel. We're going to do an overbuild. And then on this overbuild, we're going to install these alkali activated anodes, which you can see there in the orange on this detail. So what they did was they came in. This was the structure just before they started working on it. You come in and they started to remove the delaminated concrete. So those were all the delaminated concrete was removed. They came in, added some new steel. In this case, they actually used epoxy coated steel in this. So they came in, added new reinforcing steel. You're going to want to make sure that this epoxy coated bar is continuous, or that it has a metallic path to your original steel. We want those anodes that you see installed there. We want these anodes to protect the epoxy coated steel and the reinforcing steel within the original abutment as well. So then they came in, they put their formwork up, and you can see there's a junction box here. That's how we're able to get all the readings from these anodes. So we have all of the anode wires running up to that junction box, and we also have the cathode wires, or the reinforcing steel wires, running up to that box, both from the epoxy coated bar external cage and the original reinforcing steel. And it comes up there. We have a data logger. There's a data logger in there so that it can monitor the data over time as well. And then this is what it looked like when it was finished, when the forms were being removed. And just another picture. And so this is actually another picture. This was, I believe, taken in I'm trying to remember if it was 2022 when this picture was taken. But in this graph here, what we're showing here is, in order to get cathodic protection, if you look at the very, very far right column, our polarization. So for NACE or AMP criteria, you want to have at least a minimum of 100 millivolt shift. And what we're seeing here is we're seeing much, much more than 100 millivolt shift in terms of CP for this abutment. And if you also look on the left side of the column at the date, so this project was originally installed in 2005. And if you look at the last time that I gathered readings from, it was 2022. So it's been over 15 years. And it is still providing, a zinc galvanic system is still providing cathodic protection to this abutment wall. So it's it's a galvanic system that does not require power, so you don't have to have any sort of external rectifiers, external power source system, and it is not susceptible nearly as much to lightning like some of the impressed current systems are as well. So there again, so this is a very similar system to the atmospheric portions of a pile. Again, it's just more like a larger overlay, or a larger jacket that's placed on an overlay here as well. And so this is just going to bring me into the conclusion. And again, for this is so for all of the areas within a pile, if you have corrosion that's occurring on a pile, what you're going to want to do is you're going to want to look at the environment. What environment is this pile in? Can we use salt water? If you can use salt water in this environment, you're going to use a Tidal Plus jacket. It's going to rely on the salt water to activate the zinc. As you move higher up, obviously you're going to have to go to an activated system because you don't have the salt water available. And everything under the water, we're using aluminum bulk anodes for it as well. So again, just a brief this is the brief summary of the jacket systems. You have a expanded zinc mesh that is good in the tidal zone, the wicking, which is allowing the activation to be brought up to a much, much higher level with the salt water, and then you go over to the activated or the alkali activated anodes that do not, or jackets that do not require any salt water as well. So very similar to that abutment project that I just showed you. So, and that basically ends it. I think I ended up just on time for it as well. So, and I don't know how you're going to do this. Did you have some questions come through?
I sure do. We actually, you really drew in some smart engineers, because we got some good questions from this group. But yeah, what we're going to do, we're going to get through a few questions here. We obviously won't get through all of them, but any of them that don't get answered, we'll be passing them on to Jason here, and then he'll be able to reach out to you and answer those after the show. But to start off with, this one was kind of a common question, and I'll kind of combine some of them together. But how long do these jacket systems typically last their service life, or how much do they extend the service life of a structure?
Typically, the jackets have a service or designed for a service life of 20 to 25 years. So again, with the Tidal Plus or the activated, because you have discrete anodes that are placed around the pile, you can actually increase the amount of anodes on there, which would also increase the service life of the jacket as well for that. But on average, 20 to 25 years is a typical life expectancy for the CP jackets.
And Robert asks, how often are the bulk anodes inspected? And is that usually something that's done in say, a biannual inspection?
Yeah, so you saw the junction boxes that were on the piles there. Some projects actually may put 5% of the pile jackets with junction boxes. Some will have 100% of the pile jackets will have junction boxes. It just really depends upon the owner. But you would end up going out to those junction boxes, and because you have your bulk anode wire that's in there, you can actually differentiate the amount of current that's coming off of your bulk anode for it. But again, as I mentioned in the specifications, when you're doing the specifications for a project, make sure to include the bulk anode in there as part of the design, because you don't want to install just one bulk anode on there for, like I said, a very large pile, because you may get a much reduced life. For example, those the zinc hull anodes, in some instances, especially down in Florida, down in the Keys, sometimes they were only getting 5 years of service life out of those hull anodes with the jackets. Those were on large piles, obviously very aggressive environment. And again, the new anode that's been designed is basically being designed for a 20 to 25 year lifespan as well. So it's going to match the jacket, but again, for a larger pile, a larger submerged zone, make sure to do a design because it may require 2 additional anodes for it.
Right. Yeah. And speaking of that anode, Kelvin was asking, being not the same as zinc, it's being aluminum, and he's probably familiar with the Galvanic series. Do you have data that shows how compatible those two systems would be, being aluminum and zinc in the same jacket system?
Yep. So that was one of the things that was really looked at, was basically the potential of the aluminum versus the zinc in there, right? And that was one concern that was brought up, or was a concern, was you didn't want to be protecting the aluminum anode or vice versa with either the alkali activated or the tidal anode or the tidal plus. And so, yeah, for anybody who wants some specific data that can actually detail out all of the research that was done on this to show that the aluminum anode that is just exposed to seawater has very, very similar potentials as all of the zinc jacket anodes that are embedded in the concrete.
Rob asks, when would you use an impressed system in lieu of a galvanic system?
So there are impressed current systems that are definitely utilized still. So for example, I just happen to be here in Florida, so FDOT still uses them on footers or pile caps. There are areas where they find a use for them, where they're maybe larger, and this is also an area where they're doing overbuilds. They're doing an external overbuild on it. They have easy access to power and so forth. And so there are some instances where impressed current will still work. For impressed current, you're going to want to make sure that the owner has the ability to maintain and monitor these systems. Impressed current systems, because it relies on a rectifier and all this external wiring and power source, it needs to be monitored and actively monitored. There's times where they go down, whether it's just power cycles, all sorts of stuff. But definitely in the last, 15, 20 years, the galvanic systems have overtaken a lot of the ICCP, especially here in North America. But again, there are definitely places for ICCP on structures as well.
Right. Adam
and then
asks,
one last note on the ICCP versus the galvanic is in terms of installation. I would say typically the galvanic systems don't require as high level of expertise to install as compared to the impressed current systems as well. So that might be another reason for it.
Okay. Adam asks, are jackets economical in non-coastal regions, for example, preserving columns that have been exposed to de-icing salts?
Yes, so we have used that many times, especially in the Midwest, where you have de-icing salts, whether it's because of the failed expansion joints, and it goes down on the roadway down below. And a lot of times you'll get a lot of corrosion that's occurring on that first 2, 3, 4, 5 feet of column that's exposed to that roadway. And what ends up happening with that as well is it makes it fairly quick. They can come in, they can just throw a jacket around it, they can fill it with mortar, and they're able to remove it fairly quickly and get an economical, quick, long-lasting repair out of it. And then one of the things that you have with that as well is when you leave that stay-in-place form in place, it also helps protect against future ingress of your de-icing salts from it.
Right. Claudio asks, regarding protection of sheet piles, what would you recommend for sheet pile walls which are exposed to fresh water and currently have notable corrosion due to maybe a coating failure or the fluctuating water levels in a moderate atmospheric corrosion environment?
And so if this is, I guess it's just going to depend if it's in the water, if it's in the water zone, you're going to have to potentially maybe an aluminum anode, but it's unlikely. You may have to go to a magnesium anode for it. And again, we would probably need the water parameters to make a recommendation for that. Or if it's on the soil side, you're definitely going to have to go to a magnesium anode on it. And then for the atmospheric area, right? If it's the atmospheric area, you cannot rely on any bulk anode, and you're going to have to do some sort of a jacket overlay, like was shown on a couple of slides there, because you have to, if you remember going back to the very, very beginning slide, one of the beginning slides, the Acme, you actually have to have an electrolyte in there, right? So you can't just hang a bulk anode on the atmospheric portion of a sheet pile wall. It has to be in an electrolyte for it.
All right, I think we got time for maybe one or two more questions here. Salma asks, why are the junction boxes optional?
That's a good question. The reason I would say that they're optional is it's a point of failure. You can take all of the anodes that are on that pile or the structure, within that pile, and you can directly connect them to the pile. By doing that, you're removing the junction box, so you're removing a point of failure. If you ever go out to a bridge, especially ports, where they have a lot of these jacket systems installed, any of these junction boxes that are kind of exposed, they have a tendency to get knocked off. And it can be even just from storm events where you have a lot of debris in the water. When you have some large debris in the water with waves, even if you try to protect those boxes, it's surprising how much damage can happen out there. And then by directly connecting it, you're just limiting the damage that can happen to it. But for example, if you were doing a structure with 100 piles, you could still do 10 of those piles with monitoring boxes, so that it still gives you the ability to come back and do some monitoring on your piles. And then as well, for any of the energizing, you can energize, or you can take readings before and after, even with direct connections. So you would basically take a measurement of the potential of your pile, your electrical potential of your pile, without the anodes attached. And then when you directly connect it, you can now measure the potential with your anodes connected. So you can still quantify and certify that the system is producing or providing cathodic protection even without junction boxes.
All right. Well, thank you, Jason. I think that's all the questions we're going to have time for today. We got so many more to go through, so we're going to pass those on to Jason after the presentation here, and he'll get back to you all. If you want to flip on to our next couple slides here, Jason will have your information for if anyone wants to reach out to you. There's his email or his phone. He doesn't sleep. He's in Florida. It's a wonderful place to be. And the final note is the recording and slides will also be made available on our website, and you'll see the link to that page is the same as where you registered, but you'll get that link again in that follow-up email. And thank you, Jason, for putting on this awesome presentation.
Yes, thanks everybody for joining.
And yes, thank you all for joining, and let's get out there and save some structures.